Hi everyone. In today's video, we're going to talk about sampling methods in graph neural networks. We will go through the papers, and at the end, I will go through a notebook to see how to use sampling methods on a graph neural network using pytorch-geometric library. So let's get started. I'm not gonna lie, but this was one of the most difficult topics I've read about. And it's because that most of the survey papers in this field, they have three categorization. The first category is node sampling. Second category is layer-wise sampling, and the third category is subgraph sampling. But in fact, all of these categories, they are passing a subgraph to the graph neural network. And this was the most confusing part because all of these methods, they are passing a subgraph to the graph neural network. So categorizing them based on node sampling or layer-wise sampling is a bit confusing. So it took me a while just to get my head around this. And that's why I don't rely on survey papers to read about any topic. Because survey papers, they have to use some categorization to categorize methods. But this categorization is not necessarily clear. Sometimes it's confusing the reader. So in the papers that we are going through them in a chronological order from the oldest paper to the newest papers. Just before we go through the sampling methods in graph neural network, sampling graphs is not a new idea. It has been used in computer science research for decades. Let's go through some old papers, just a warm-up for the graph neural network sampling. The first paper here is the clustering using similarity measure based on shared near neighbors. This paper came out in November 1973. So you probably noticed that in my videos, I like to bring old papers. And it's basically because I would like to, it's an acknowledgement for the pioneers in computer science research. And another part that these papers in the 80s, 90s, and early 2000s, they explain the fundamentals in a very clear way. So what this paper is doing, it's here they provide the matrix for the near neighbor list. Each row is a node, and the column is its nearest neighbors. The first entry is the 0th neighbor, which is the point itself, then the nearest neighbor, the second nearest neighbor, all the way to nth nearest neighbor. This doesn't have to go all the way to nth nearest neighbor. You can just cut it off to the kth nearest neighbor. It depends on what you need, just to save up on storage. So once they have this near neighbor list, they start matching rows to find shared nearest neighbor. And at the end, they created an n by n matrix, which is the adjacency matrix of the shared near neighbors. So for example, node number 1 has 3 shared neighbors with node number 7. So here is the circle for node number 1. It shares 10, 11, and 7. 3 shared neighbors between 1 and 7. And 7 also shared 3 neighbors with 1, which is 1, 11, and 10. So they construct this adjacency matrix. This paper is not directly related to graph neural network sampling. But when I read about how graph neural network sampling is started, it starts by selecting a node and then connecting to neighbors and connecting to the neighbor's neighbors. So the first thing that comes to my mind is this paper. So I thought bringing this paper into this discussion would be a great starting point. So this is the shared nearest neighbor paper. Another method for sampling nodes on the graph. So in the early 2000s, spectral clustering became very popular. This is the main reference on spectral clustering. It's called a tutorial on spectral clustering by von Luxburg. And if you look at the spectral clustering algorithm, it relies on constructing a similarity matrix, which is an n by n matrix. So constructing the similarity matrix, which is the adjacency matrix, and performing eigendecomposition on that matrix to find the clusters for spectral clustering. So constructing this adjacency matrix would be very large because if n is large, then n by n is growing exponentially. And even performing eigendecomposition requires O n cube. So these computational demands are very heavy. And what people are started doing, they started doing approximating on the graph, sampling, just randomly sampling on the graph, or just approximating on the graph. One of the well-known methods in approximate spectral clustering is past approximate spectral clustering. So here they are suggesting performing k-means on all the points in the dataset, from x1 all the way to xn, and to get k centroids, from y1 all the way to yk. Performing spectral clustering, it won't take place on the whole dataset. It will take place on the centroids. And after you cluster the centroids, you recover the cluster membership for each xi by looking up the cluster membership of the corresponding centroid yj in the correspondence table. So first you just approximate the points in the dataset using k centroids. Then you perform spectral clustering on these centroids. Then you just propagate back the cluster membership from the centroids to the points in the dataset. Another method for approximating spectral clustering, it's called spectral grouping using Nystrom method. So they got a good figure here. Here, this is spectral clustering was very popular in doing image segmentation. So here, the first method is just using the dense affinity matrix, which is n by n matrix, and performing eigen decomposition to get the final segmentation, or just get the approximated affinity matrix using Nystrom method, then perform image segmentation. So what is the Nystrom method? I found a good explanation here in scikit-learn documentation. They say while the computational complexity of the exact method is O n cube, n is the number of points in the dataset, the complexity of the approximation is O n components. I found n components and n samples is very confusing. So let's call n samples n, which is the number of points in the dataset, and n components, let's call it m, where m is much smaller than n. So m is the number of representatives, number of centroids, number of sampled points. It's a subset of points. It's much smaller than n. So we are going down from O(n) cube all the way to O(m) squared times n, where one said that m is much smaller than n without significant decrease in the performance. So this is the adjacency matrix. K11, it's the small set. It's a small affinity matrix, the representatives affinity matrix, how the representatives are connecting to each other. It's either the distance between them or the similarity between them, but this is very small affinity. K12, it's the similarity between the representatives and the rest of the points in the dataset. K21, it's the similarity between the representatives and the rest of the points in the dataset. But here is the bottleneck. K22, it's a similarity matrix of the all points in the dataset. So to avoid computational bottleneck, it's just avoid computing K22. So K22 can be approximated using this term here. So the whole adjacency matrix can be approximated from these three parts, which are very small compared to this part of the adjacency matrix. So this is how Nystrom method can approximate the adjacency matrix. So we got two methods to reduce the computations for spectral clustering. You can run k-means on points, or you can use Nystrom method. I've done approximate spectral clustering research myself. So in my PhD, we just write this paper, approximate spectral clustering with eigenvector selection and self-tuned K. So for basically we are running k-means on these points to find these representatives. They called representatives, and our job is just to find a good similarity between these two representatives. The similarity can be the distance, it can be the number of shared points. It basically can be anything. So we noticed that node approximation doesn't work for all datasets. So for example, in another paper, we took these two datasets. The one on the left clearly has 5 clusters. It's one sparse cluster and 4 dense clusters. And another dataset with one outer ring and two dense clusters are almost touching the ring. So if you try to do node approximation on these two data sets, you basically cannot get a disconnected graph. So these representatives will be connecting to these representatives, and here on the edge of the cluster, they will be connected to the other cluster. So we came up with a method that produces these two graphs. Basically, we kept the same number of nodes. We didn't reduce the number of nodes, but we relied on reducing the number of edges to make a very sparse adjacency matrix and a very efficient spectral clustering. So how did we get this clean graph? So here, for example, for this point, we start with seven neighbors. We compute the mean and standard deviation. Then we start adding more neighbors. If the mean stays within the standard deviation range, it didn't just exceed the standard deviation. This means we can keep adding more neighbors. But if this distribution becomes flatter, then we are just leaving our neighborhood into a new neighborhood. So for example, for this point, when it starts connecting to these points around it, it has a similar distribution as the baseline distribution, which is with 7th neighbors. So we keep adding points, but once it touches this cluster, this distribution becomes flatter, and the mean just exceeds the standard deviation of the baseline distribution. Then we cut. Then we stop adding more neighbors. So by following these local statistics, we were able to produce this graph. We start with a k nearest neighbor graph. Then we start removing edges just to get this clean graph. So this was a historical background on doing sampling or doing approximation on graphs using spectral clustering. Now let's move to graph neural networks and see how sampling is done. But before I jumped into the papers, I just want to read about why do we need sampling for graph neural networks. So if you go to FastGCN paper, Fast Learning with Graph Convolution Networks via Importance Sampling. If you go down here into section 3, they explained very clearly why do we need sampling to perform stochastic training for graph neural networks. So training and inference through sampling. One striking difference between GCN and many standard neural network architectures is the lack of independence in the sample loss. Training algorithms such as SGD, stochastic gradient descent, and its best generalization are designed based on the additive nature of the loss function with respect to independent data samples. For graphs, on the other hand, each vertex is convolved with all its neighbors, and hence defining a sample gradient that is efficient to compute is beyond straightforward. So in points, in standard neural networks, points, images, these samples are independent. They do not rely on each other, but in graphs, each vertex is allowed to connect to any vertex on the graph. So it is dependent on that vertex. So here they talked about stochastic gradient descent for standard neural nets. So one may interpret that each gradient step makes progress toward the sample loss, the gradient giving a learnable parameter and a sample that we introduce to the network. The sample loss and the sample gradient involve only one single sample, xi. But for graphs, one may no longer leverage the independence and compute the sample gradient, discounting the information of i's neighboring vertices and their neighbors recursively. We therefore seek an alternative formulation in order to cast the learning problem under the same sampling framework. Let's assume that there is a possibly infinite graph, G prime, with the vertex set V prime associated with the probability space V prime Fp. So what this paragraph is saying that we need a probability distribution to get in the independence feature that is needed for stochastic gradient descent. So here they changed the GCN architecture. This is the original GCN architecture. They introduced the probability distribution into the GCN architecture. So this is the FastGCN paper. And this section here just explains why do we need sampling for graph neural networks. The first paper on sampling on graph neural networks is called Inductive Representation Learning Large Graphs, or it is known as GraphSAGE. So what this paper is introducing, sampling neighborhoods. So given seed points, this is the seed point in this example. First, for the first hop of GCN, we will sample direct neighbors. So we are sampling 3 neighbors and we are excluding these 2. And for the second hop of the GCN, we are sampling the neighbors of neighbors. So with each hop of GCN, with each layer of GCN, we are sampling the neighbors. And if we done that for the number of seed points, we can end up with subgraphs that can be used for training the GCN. So usually you go through all the nodes in the graph and you just chop them into subsets and treat each subset as seed nodes. And for each seed nodes, you basically perform this. So for each group of seed nodes, you are getting a subgraph that is used to train the GCN. Then you move to the next group of seed nodes and you train the GCN on that subgraph. So we are feeding subgraphs to the GCN. But in FastGCN, they changed the sampling technique and they rely on the layers. So for each layer L, sample uniformly TL vertices U1 all the way to UTL. So for each layer, we are sampling a fixed number of nodes. We don't rely on the neighboring connections. We rely on the presence in each layer. But these 2 methods, FastGCN and GraphSAGE, they have some problems. These problems is highlighted in this paper, layer-dependent importance sampling for training deep and large graph convolutional networks. So here they have a very good figure here. So in GraphSAGE, these are 2 seed points, and the blue nodes are their direct neighbors. This node here can be sampled twice, and its feature vector will be added here to this node, and it will be added here to this node. And this is not good for training because this node will have a larger influence on training, and this node that did not get sampled, it won't have any influence on training. And in FastGCN, because the sampling does not account for neighboring connections, FastGCN will sample nodes outside of the neighborhood, just like these 2 nodes. The layer-dependent importance sampling, ladies, that it solved these 2 problems, and the algorithm here. So they started from the last layer to the first layer, and for each layer they get the layer-dependent Laplacian matrix, and they calculate the sampling probability for each node. Another method for sampling on graph neural networks is ClusterGCN, an efficient algorithm for training deep and large graph convolutional networks. I explained this paper in my last video, GNN mini batch, but I'll just go through it here. So they used clustering algorithms to partition the graph, Metis or Graculus, and they get the graph clusters from these 2 algorithms, and they order the adjacency matrix in this way, in a block diagonal order, and they merge the number of blocks together, number of subgraphs together, and they feed these subgraphs, group subgraphs, into the graph neural network as one batch. And they train the graph neural network in this manner. I've read a paper that says that a problem that clustering is not included in training, so the method removes edges before starting training. Yeah, that's a problem, but there is another problem with the ClusterGCN. So I got in my notes here. So if this is a cluster of nodes, This is clearly a cluster, and this is another cluster. This node here will be forced to be in one of these two clusters, because after ordering the GCC matrix as a block diagonal matrix, the off diagonal edges will be cut. So for this node, it will be merged with this cluster and cut these edges, or it will be merged to other cluster and cut these edges. I didn't run an experiment, but I'm not sure if this happens a lot in the graph. What are the consequences? I'm not sure. But this situation might happen in ClusterGCN. The last method I'm going through here is a GraphSAINT, graph sampling based inductive learning method. So they have changed the probability distribution for sampling. As they say, before training starts, we run the sampler repeatedly to obtain a set of n subgraphs G. We set up a counter, CV and CUV, a counter for each node in the graph and a counter for each edge in the graph, for each vertex in V and for each edge in E, to count the number of times of node or edge appears in the subgraphs of G. Then we set alpha UV to be the counter of the edge divided by the counter of the node, and lambda V to be the counter of the node divided by the number of subgraphs that are sampled. So they used alpha and lambda to derive samplers for variance reduction. If the variance is reduced, then this leads to a good training. Now it's the time for the code. So I would like to acknowledge the help of pytorch-geometric tutorials. I brought some code from there, and here's the piptech entry for pytorch-geometric paper. Most of the sampling methods need torch sparse, and torch sparse can be installed using this command here to install pytorch geometric dependencies. But this command depends on the whether you're working on the CPU or you're working on the GPU. So here I'm working on the CPU version of Google Colab. So and this is the torch version. So you just plug in the torch version, and if you're working on the CPU, just type CPU, and if you're working on the GPU, just type your CUDA version. So here I'm importing some libraries. I'm setting the random seeds, and here I am creating a synthetic dataset using stochastic block model from pytorch-geometric. This is basically an affinity matrix between the points within the three clusters. So we want the probability of connecting with the points on the same cluster to be 10%, and the probability of connecting to other clusters can be 5% or 2%. So here is the data set. Note that these are not the actual position, because the actual positions are 10-dimensional here. These are mapping done by Network X Spring Layout. But it shows that there is an overlap between the orange and blue cluster. So here is how batch training for GCN. So if it's full batch, we are feeding the whole graph with a set of vertices and set of edges to compute the loss. But if it's a mini batch, then we are splitting the graph into subgraphs and feeding the sets of vertices and edges independently. So for each step, for each iteration in the epochs, we are feeding a subgraph to compute the loss. The first sampler is neighbor loader. Neighbor loader produces subgraphs GS sampled from the original graph. So the number of subgraphs is determined by the batch size, the number of seed nodes, and the number of nodes in G. So the number of nodes in G divided by the number of seed nodes. So for example, here in this loader, we are setting the batch size to be 128, and the number of nodes is 1,500 divided by the batch size, which is 128. gives us 11.7. This means the last batch doesn't have 128 seed points, but in total we are getting 12 subgraphs. So if we enumerate over this loader here, and for each subgraph we're printing the feature matrix and the edges list, we are getting 12 subgraphs, each of which has its own feature matrix and its own edges list. We are using these 12 subgraphs to train the GCN for a number of epochs. So for each epoch, we are feeding these 12 subgraphs. These 12 subgraphs, they might have overlap between them because we are starting from seed points and we're connecting to their neighbors, then we're connecting to their neighbors' neighbors. So if we plot the first 3 subgraphs with this loader here, how do they look like? So if you see that the nodes in white, these are not selected for this subgraph. So for this first subgraph, the second subgraph, the third subgraph, these white nodes were not selected. So there's a trade-off in neighbor sampler, balancing the trade-off between the batch size and the number of subgraphs. Setting the batch size to a small number increases the number of subgraphs. So if we start with a small number of seed nodes, this means that we need more subgraphs to cover all the seed nodes. But each subgraph would have a small number of nodes because we are sampling from a smaller subset of seed nodes. But if we select large number for a batch size, this leads to a smaller number of subgraphs, but each one has more nodes because we are sampling from a large pool of seed nodes. So here is a comparison between batch size of 32 seed points or 128 seed points. So if we use a batch size of 32, the number of nodes is 1,500 divided by 32. This gives us 46.8. So in total we would have 47 subgraphs. But if we use a batch size of 128, we got 12 subgraphs. Here I plot the first 3 subgraphs for batch size equals 128, and the first 3 subgraphs for a batch size equals 32. So this is the comparison here. See that in a neighbor sampler with the batch size 32, there are more white nodes because these nodes were not selected. So the graphs, if we reduce the batch size, we ended up with a sparse adjacency matrix. We ended up with a small subgraphs. So you have to balance the trade-off. Do you want more subgraphs, but each one is small, or do you want large, fewer subgraphs, but they are very dense? So this is the trade-off between the number of subgraphs and the batch size. This is for the neighbor sampler. The next sampler is the cluster load. The cluster loader is in the cluster loader, the graph is partitioned using Metis algorithm into number of partitions specified by the number of parts. Here is the number of parts. So then these partitions are grouped into batches where each batch contains partitions specified in batch size. So just a note here that the word batch loses its meaning. I prefer to use subgraphs rather than batch because batch for the neighbor sampler batch is used the number of nodes, the number of seed nodes. But here batch size is used on the number of clusters that form the subgraph. So it means different things, and don't focus on that because it might be confusing. So the number of subgraphs in cluster loader determined by the number of partitions, how many clusters we have, and batch size. Are we grouping more clusters or are we grouping fewer clusters? So the total number of partitions divided by the batch size. So here we're setting the number of partitions to be 128 and the batch size is 32. So we are getting 128 clusters and we are grouping each 32 of them into one batch. So 128 divided by 32, we got 4 subgraphs that will be used to train the GCN. So you feed your data set here and you set the number of parts to get the cluster data. Then the cluster loader will group the cluster data into a number of batches. So if we enumerate over this loader, these are the subgraphs, and these are the nodes and edges list. This is the cluster loader. You might notice that the position have changed. That's because I'm forming a new graph using network X. In neighbor loader, it used to return the global indices. These are the global indices. N_ID. These are the global indices. The indices using the main, the indices using the original feature matrix and the original adjacency matrix. But in cluster loader, these indices are not retained. So I have to create another graph using network X. But here you can see that these subgraphs capture the data set in a way that the blue and orange cluster are overlapped and the green cluster is just further apart from them. So here is a trade-off in cluster and loader. The trade-off between number of partitions and the batch size. Sending the number of partitions to a smaller number leads to larger clusters with more nodes. So if you ask for fewer clusters, then the metis will just group large number of points into one cluster. On the other hand, setting the batch size to a large number increases the number of nodes in the subgraph. So if you group more cluster into one batch, this will also increase the size of the subgraph. But these nodes are not necessarily in the same cluster because the batch size represents a group of clusters made into one subgraph. If we increase the number of partitions to be 256 and we keep the batch size to the same number, which is 32, let's see what happened here. So this is the number of parts, 128, batch size 32, and here number of parts is 256 and batch size is 32. It's a fewer points because we asked for more clusters, but we kept the batch size the same. And this is the problem that might arise from using ClusterGCN. This point will be forced to be in one of these two clusters. The last sampler here we used is the GraphSAINT sampler. So the GraphSAINT sampler samples the number of subgraphs based on the number specified and the number of parameters, number of steps. So here you are explicitly asking for the number of subgraphs. The number of subgraphs is not computed for you just like a neighbor loader or ClusterGCN. In a GraphSAINT sampler, you are asking for explicitly number of subgraphs. And this number of subgraphs will be sampled using node sampler, edge sampler, or random walk sampler. Let's look at the implementation in pytorch-geometric. So this is the class for GraphSAINT sampler. It basically applies the counter, the edge counter, the node counter, the edge counter mentioned in the paper. These two counters, CV and CUV, are here. So pytorch-geometric uses this class to return the normalized nodes and normalized edges. Then it used the following classes: GraphSAINT node sampler, GraphSAINT edge sampler, and GraphSAINT random walk sampler to sample from the GraphSAINT sampler. So GraphSAINT sampler is used to prepare the sampling probabilities, then how would you like to sample from the graph? So this is how it's implemented in pytorch-geometric. So here I've used the node sampler, the edge sampler, and the random walk sampler with the batch size equals 256. This is not, it won't get you 256 nodes from the graph. This is the approximate number of the nodes that you might get. A number of steps, I'm asking for 4 subgraphs for each of these loaders. The walk length for the random walk, how many hops that we are jumping from the original node, I'm setting it here to be 2. It's the same number of it's the usual number for GCN layers. So 4 graphs for the node sampler, 4 graphs for the edge sampler, 4 graphs for the random walk. You can notice that the node sampler has the least number of nodes, and edge sampler and random walk sampler have more nodes in them. And they also have more edges in them. So let's plot these 4 graphs. So these are the sampled by node sampler. These are sampled by the edge sampler. These are sampled by the random walk sampler. I don't know, but for me, I think the edge sampler captured the original dataset better here. I don't know, but yes, that's it, guys, for today's video. If you find this video helpful, please like and subscribe. By the way, you can find a link to the notebook I'm working on in the description below. Thanks for watching. Bye.